Okay, so now let us look at this question. So this question, it asks, write down the PMF or the PDF for the following distributions, and also, the applications. So we give you one example that is, for the Pascal distribution, it relates to the random experiment of the repeated independent trials until observing M successes. So in other words, for example, if you toss a coin and then until you do this coin tossing repeatedly until you observe, let's see, M heads. Okay, so that's how do you explain that. So first one, it's the Bernoulli distribution here. Bernoulli distribution, first of all, this Bernoulli distribution stands for, you only have two outcomes. Okay, so the simplest one is, you toss a coin. The outcome, you only have two outcomes, and it's either head or tail, right? So that's the simplest discrete random variable. So for the first one, Bernoulli distribution here, and then first of all, this is going to be a discrete random variable here. So we said that x is a Bernoulli random variable with a parameter p. So this parameter, it's you can think about it, it's called the success probability. So for and then so typically we'll just write it into this one. And then, so since this is a discrete, right, random variable, so correspondingly it's gonna have a probability mass function. So it's a PMF. It's gonna be given as, so it's a P when x equals 1, and it's 1 minus P, x equals 0. Okay, and then otherwise. Okay, otherwise. Okay. So as you can see that, so there is this Bernoulli random variable. You can only take either 1 or 0, those two possible values. Okay. And the application, as we see that it's it models the random experiment that has two possible outcomes. Okay. So For example, you take a test, and then this test either, you're gonna pass or fail. Okay. And yeah. So that's the first one. Second one, geometric distribution here. And talking about geometric distribution here, so this is kind of like a related with the Bernoulli distribution. But what it does is, for example, still if we stick with the example that you toss a coin, all right, and then we want to know that the number of the coin tosses, until I observe the first hand. Okay, observe the first hand. So you can think about it. The geometric distribution is it's an experiment as like the repeating Bernoulli trials until you observe the first success. Okay, until the first success. Okay. And then the X stands for the total number of repeating in this experiment. So again, for example, if we take the idea of toss the coin, and then X is going to be the total number of the coin tosses, in this experiment. And of course, as you can see that if you toss a coin, it's very possible the first time you already observe, let's see, a head, right? Or second time you observe the head, then it's going to be, the first time it's going to be tail, then the second time it's going to be head. Or, if X equals 3, you're going to have tail, and then head, right? So the again, this is a discrete. So it's we always write this as the geometric P. P stands for the successful probability. Okay. So it's a PMF. Is going to be like in terms of K. Okay, K is the number of the repeating in this experiment. K, of course, we know that it can be 1, 2, 3, ... right? And so it's going to be P times 1 minus P to the power of K minus 1. So you can think about it, so you have K times, and then you get your first success. In other words, the first K minus 1 trials is going to be all failure. So it's going to be 1 minus P to the power of K minus 1, and then times P. Okay, the K's time, you got it. And of course, K here equals 1, 2, 3, and also 0 otherwise. Okay, otherwise. So that's what we call about the geometric distribution. Binomial. Binomial distribution, it says like this, okay? It says like this. So this time, it's we're still gonna need the Bernoulli trial. So let's still stick with the toss the coin, okay? So differently is, right now, we're gonna toss the coin n times, okay? And then, so keep in mind, each coin toss is gonna be a Bernoulli, and then so we're gonna need this probability p, okay? And meanwhile, I also need another parameter called n. Here, it's the I toss this coin n times or repeated this trial n times here. So the number of the variable, what I defined it here, you can think about it, it's the total number of successes, okay, observed in trials, okay. So as you can see that for this, what is like the range for this x here? So the range, as you can see, it can be 0, right? In other words, if we're still using the Hill test, the head and tail, if we let the probability of we have a head is p, tail is going to be 1 minus p. When x equals 0, that means you're going to have all tails, right? Tail, 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 tail. Of course, so that the range for the x can start from 0, 1. And then as you observe, the largest number you can see is going to be n. That means all this n, coin tossing is going to be all head, okay? So this is what we call a binomial distribution, okay? So this random experiment, it behind the binomial distribution, okay? So and basically we're gonna write it into binomial n of p here, okay? And easy to notice that so again, this is still a discrete case here, and the PMF for this part, as you will see here, is so this part is going to be a combination one, right? So you have n chooses k, and then so you have p to the power of k, and then the n minus k part is going to be 1 minus p to the power n minus k, k starting from 0, 1, 2, dot, 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 up to n, and then 0 otherwise, right? Otherwise, okay. Okay, so that's a combination process. So it's n chooses k, and then yeah, that's the first 3 parts. Okay, so I'll stop here. Then I'll see you soon.